Hello, I am Maureen Pinades from BSF Math 3B, and I will discuss about testing the difference between two variances in chapter 9-5. Statisticians are also interested in comparing two variances or standard deviations. For example, is the variation in the temperatures for a certain month for two cities different? For the comparison of two variances or standard deviation, an F-test is used. If two independent samples are selected from two normally distributed populations in which the variances are equal, denoted by sigma squared sub 1 is equal to sigma squared sub 2, and if the variances s squared sub 1 and s squared sub 2 are compared as s squared sub 1 all over s squared sub 2, the sampling distribution of the variances is called the F distribution. So here are the characteristics of the F distribution. Number 1, the values of F cannot be negative because variances are always positive or 0. Number 2, the distribution is positively skewed. Number 3, the mean value of F is approximately equal to 1. And number 4, the F distribution is a family of curves based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the variance of the denominator. The shapes of several curves for the F distribution is this. Here is the formula for the F test. F is equal to s squared sub 1 all over s squared sub 2, where the larger of the two variances is placed in the numerator regardless of the subscripts. The F test has two terms for the degrees of freedom, that of the numerator, wherein n sub 1 minus 1, and that of the denominator, n sub 2 minus 1, where n sub 1 is the sample size from which the larger variance was obtained. When you are finding the F-test value, the larger of the variances is placed in the numerator of the F formula. This is not necessarily the variance of the larger of the two sample sizes. Table H in Appendix C gives the F critical values for alpha 0.005, 0.01, 0.025, 0.05, and 0.10. Each value involves a separate table in Table H. These are one-tailed values. If a two-tailed test is being conducted, then the alpha over 2 value must be used. For example, if a two-tailed test with alpha is equal to 0.05 is being conducted, then the 0.05 is divided by 2, we will get 0.025. Then 0.025 table of Table H should be used. To understand further, we will use the example in 9-12. And here is the example. Find the critical value for a right-tailed F-test when alpha is equal to 0.05. The degrees of freedom for the numerator, abbreviated DFN, are 15, and the degrees of freedom for the denominator, DFD, are 21. So here is the solution. Since this test is right-tailed with alpha is equal to 0.05, use the 0.05 table. The DFN is listed across the top and the DFD is listed in the left column. The critical value is found where the row and column intersect in the table. In this case, it is 2.18. As noted previously, when the F-test is used, the larger variance is always placed in the numerator of the formula. When you are conducting a two-tailed test, alpha is split. And even though there are two values, only the right tail is used. The reason is that the F-test value is always greater than or equal to 1. To understand further, this is another example. Find the critical value for a two-tailed F-test with alpha is equal to 0.05 when the sample size from which the variance for the numerator was obtained was 21, and the sample size from which the variance for the denominator was obtained was 12. Here is the solution. Since this is a two-tailed test with alpha is equal to 0.05, the 0.05 is divided by 2. Then, we get 0.025. 0.025 table must be used. Here, DFN is equal to 21 minus 1 is equal to 20. And DFD is equal to 12 minus 1 is equal to 11. Hence, the critical value is 3.23. So, here is the table of alpha is equal to 0.025. And the intersection of 20 and 11 is 3.23. When you are testing the equality of two variances, these hypotheses are used. First is right-tailed, wherein null hypothesis is sigma squared sub 1 is equal to sigma squared sub 2. And the alternative hypothesis is sigma squared sub 1 is greater than sigma squared sub 2. And the left-tailed is the null hypothesis sigma squared sub 1 is equal to sigma squared sub 2. And the alternative hypothesis is sigma squared sub 1 is less than sigma squared sub 2. And the two-tailed is the null hypothesis, sigma squared sub 1 is equal to sigma squared sub 2. And the alternative hypothesis is sigma squared sub 1 is not equal to sigma squared sub 2. There are 4 key points to keep in mind when you are using f-test. First is the larger variance should always be placed in the numerator of the formula, regardless of the subscripts, wherein f is equal to s squared sub 1 all over s squared sub 2. For a two-tailed test, the alpha value must be divided by 2, and the critical value placed on the right side of the f-curve. Number 3, if the standard deviation instead of the variances are given in the problem, they must be squared for the formula for the f-test. And lastly, when the degrees of freedom cannot be found in table H, the closest value on the smaller side should be used. Here is the assumptions for testing the difference between two variances. First, the population from which the samples were obtained must be normally distributed. Note, the test should not be used when the distributions depart from normality. Number 2, the samples must be independent of each other. Remember also that in test of hypothesis using the traditional method, these 5 steps should be taken. First is step the hypothesis and identify the claim. Step 2, find the critical value. Step 3, compute the test value. Step 4, make the decision. And step 5, summarize the results. To understand further, here is another example in 9-14. Heart rates of smokers. A medical researcher wishes to see whether the variance of the heart rates in beats per minute of smoker is different from the variance of heart rates of people who do not smoke. Two samples are selected, and the data are as shown using alpha is equal to 0.05. Is there enough evidence to support the claim? Here is the data. Smokers, wherein n sub 1 is equal to 26, and s squared sub 1 is equal to 36. Non-smokers, wherein n sub 2 is equal to 18, and s squared sub 2 is equal to 10. We will use the 5 steps in traditional method to solve this problem. So, step 1, state the hypothesis and identify the claim, wherein the null hypothesis sigma squared sub 1 is equal to sigma squared sub 2, and the alternative hypothesis is sigma squared sub 1 is not equal to sigma squared sub 2. Step 2, find the critical value. Use the 0.025 table in table H, since alpha is equal to 0.05, and this is a two-tailed test. Here, DFN is equal to 26 minus 1 is equal to 25, and DFD is equal to 18 minus 1 is equal to 17. The critical value is 2.56. DFN is equal to 24 was used. Here is the table using alpha is equal to 0.025, and the intersection of 24 and 17 is 2.56. Step 3, compute the test value, wherein f is equal to s squared sub 1 all over s squared sub 2 is equal to 36 all over 10. Then we get 3.6. Step 4, make the decision. Reject the null hypothesis, since 3.6 is greater than 2.56. Step 5, summarize the results. There is enough evidence to support the claim that the variance of the heart rates of smokers and non-smokers is different. Here is another example. Waiting time to see a doctor. The standard deviation of the average waiting time to see a doctor for non-life-threatening problems in the emergency room at an urban hospital is 32 minutes. At the second hospital, the standard deviation is 28 minutes. If a sample of 16 patients was used in the first case and 18 in the second case, is there enough evidence to conclude that the standard deviation of the waiting times in the first hospital is greater than the standard deviation of the waiting times in the second hospital? Here is the solution. Step 1 is to state the hypothesis and identify the claim, wherein the null hypothesis sigma squared sub 1 is equal to sigma squared sub 2, and the alternative hypothesis is sigma squared sub 1 is greater than sigma squared sub 2. Step 2, find the critical value. Here, dfn is equal to 16 minus 1 is equal to 15, and dfd is equal to 18 minus 1 is equal to 17. From the 0.01 table, the critical value is 3.31. So here is the table. The intersection of 15 and 17 is 3.31. Step 3, compute the test value using the formula f is equal to s squared sub 1 all over s squared sub 2. Then is equal to 32 squared all over 28 squared. Then we will get 1.31. Step 4, do not reject the null hypothesis since 1.31 is less than 3.31. Step 5, summarize the result. There is not enough evidence to support the claim that the standard deviation of the waiting times of the first hospital is greater than the standard deviation of the waiting times of the second hospital. In finding p-values for the f-test statistic is somewhat more complicated since it requires looking through all the f-tables in Table H in Appendix C using the specific DFN and DFD values. For example, suppose that a certain test has f is equal to 3.58, DFN is equal to 5, and DFD is equal to 10. To find the p-value interval for f is equal to 3.58, you must first find the corresponding f values for dfn is equal to 5 and dfd is equal to 10 for alpha is equal to 0.005, wherein alpha is 0.10, the f is 2.52 in page 790. When alpha is equal to 0.05, f is 3.33 in page 789. When alpha is equal to 0.025, f is equal to 4.24 in page 788. When alpha is equal to 0.01, f is equal to 5.64 in page 787. When alpha is equal to 0.005, f is 6.87 in page 786. Now, locate the two f values that the test value 3.58 falls between. In this case, 3.58 falls between 3.33 and 4.24, corresponding to 0.05 and 0.025. Hence, the p-value for a right-tailed test for f is equal to 3.58 falls between 0.025 and 0.05. That is, 0.025 is less than p-value less than 0.05. For a right-tailed test, then you would reject the null hypothesis at alpha is equal to 0.05, but not at alpha is equal to 0.01. The p-value obtained from a calculator is 0.0408. Remember that for a two-tailed test, the values found in table H for alpha must be doubled. In this case, 0.05 is less than p-value less than 0.10 for f is equal to 3.58. Here is another example in 9-16, airport passengers. The CEO of an airport hypothesizes that the variance in the number of passengers for American airports is greater than the variance in the number of passengers for foreign airports, at alpha is equal to 0.10. Is there enough evidence to support the hypothesis? The data in millions of passengers per year are shown for selected airports. Use the p-value method. Assume the variable is normally distributed. Here is the data. American airports is 36.8 and 72.4, 60.5, 73.5, 61.2, and 40.1. Foreign airports 60.7, 40.7, 51.2, and 38.6. Solution. Step 1 is state the hypothesis and identify the claim, wherein the null hypothesis is sigma squared sub 1 is equal to sigma squared sub 2, and the alternative hypothesis is sigma squared sub 1 is greater than sigma squared sub 2. So this is the claim. Step 2, compute the test value using the formula in chapter 3 or a calculator. Find the variance for each group. Then s squared sub 1 is equal to 246.38 and s squared sub 2 is equal to 95.87. Substitute in the formula and solve. F is equal to s squared sub 1 all over s squared sub 2. Then is equal to 246.38 all over to 95.87. Then we get 2.57. Step 3, find the p-value in table H using dfn is equal to 5 and dft is equal to 3. When alpha is equal to 0.10, f is 5.31. If alpha is 0.05, f is 9.01. If alpha is 0.025, f is 14.88. If alpha is 0.01, f is 28.24. If alpha is 0.005, f is 45.39. Since 2.57 is less than 5.31, the p-value is greater than 0.10. The p-value obtained from a calculator is 0.234. Step 4, make the decision. The decision is not to reject the null hypothesis, since p-value is greater than 0.10. Step 5, summarize the results. There is not enough evidence to support the claim that the variance in the number of passengers for American airports is greater than the variance in the number of passengers for foreign affairs. If the exact degrees of freedom are not specified in table H, the closest smaller value should be used. For example, if alpha is equal to 0.05 and it is a right tail test, dfn is equal to 18 and dfd is equal to 20. Use the column dfn is equal to 15 and the row dfd is equal to 20 to get f is equal to 2.20. Here is the table, and the intersection of 15 and 20 is 2.20. Note, it is not absolutely necessary to place the larger variance in the numerator when you are performing the f-test. Critical values for left-tailed hypothesis test can be found by interchanging the degrees of freedom and taking the reciprocal of the value found in table H. Also, you should use the quotient when performing the f-test since the data can run contrary to the hypothesis on rare occasions. For example, if the hypotheses are h sub o, wherein sigma squared sub 1 is less than or equal to sigma squared sub 2, written by h sub o is sigma squared sub 1 is equal to sigma squared sub 2. And h sub 1 is sigma squared sub 1 is greater than sigma squared sub 2. But if s squared sub 1 is greater than s squared sub 2, then the f-test should not be performed and you would not reject the null hypothesis. So before I end up my report, I want you to leave this quote. The only way to do great work is to love what you do. If you haven't found it yet, keep looking. Don't settle. As with all matters of the heart, you'll know when you find it. By Steve Jobs. That's all. Thank you and God bless.